Good afternoon, ladies and gentlemen. My name is Chong and I'm from Chong Institution, Singapore. Today I shall be presenting the project, the synthesis of chalcone-ligted osmium carbonyl clusters as potential bioimaging agents. Now, I did this project with a schoolmate of mine, Chong, but unfortunately he has been unable to attend the event today. Thus, I shall be presenting it. So first, let me introduce this project. We are mainly dealing with two compounds, chalcones and osmium carbonyl clusters. Now, the first compound, chalcones, are basically a class of organic compounds with the following chemical structure. They are shown to have great medical potential as they have antibacterial, anti-inflammatory, anti-cancerous, and anti-malarial properties. However, their usage in these areas have been limited, as the mechanisms that they make use of behind these properties are largely unexplored. So next, osmium carbonyl clusters. They are compounds that are made up of the tri-osmium core, with each osmium being bonded to 4 carbon monoxide ligands. Now, these carbonyl stretching vibrations give off strong mid-range infrared signals, meaning that these compounds can be viewed using IR microscopes. And they also enter cells with ease, meaning that they have potential use as bioimaging agents. This means that the cell activity could be observed without affecting the cell. So this brings us on to our rationale. Since we know that chalcone usage has been limited, since they cannot be seen in action, and we also know that osmium carbonyl clusters can be viewed using an IR microscope, we intend to investigate whether osmium carbonyl clusters with attached chalcones can be used as bioimaging agents. So for this project, we shall be first synthesizing the chalcones, then reacting them with the osmium carbonyl clusters. Now, we know from publications that osmium carbonyl clusters can react with carboxylic acid groups. Thus, we shall be synthesizing carboxylated chalcones. Carboxylic acid group is the image shown here. And finally, we shall be testing these compounds for their effectiveness as bioimaging agents. So we started this project in June, and to date, we have completed the synthesis of the chalcones, and we have also reacted them with the osmium clusters. So for the first synthesis step, we shall be synthesizing the chalcone that we need, which is the 2'-hydroxy 4-carboxylated chalcone. This is our reaction scheme. For starting materials, we are using 4 formal benzoic acid and 2'-hydroxy acetophenone with sodium hydroxide dissolved in water and ethanol, and we shall be adding hydrochloric acid after the reaction. It's performed in room temperature, and this is our expected chalcone product. So these are some images that we took during the reaction process. This is sodium hydroxide and 4-formal benzoic acid dissolved in water and ethanol. This is after the addition of 2'-hydroxy acetophenone. This is after 24 hours of reaction, and this is after acidification with hydrochloric acid. So after we performed suction filtration, we obtained the 2'-hydroxy 4-carboxylated chalcone in the form of a yellow solid shown here. So after we did a melting point test on the compound, we obtained a melting point of 249 to 252 degrees Celsius, which is very close to the literature value of 248 to 252 degrees Celsius, indicating that it's pure. The yield that we got was 75%. So after synthesizing our chalcone, we went on to synthesizing the osmium carbonyl cluster. Now we will need to synthesize this osmium carbonyl cluster OS3, CO10, and CCH32. Since it is very hard to get tri-osmium polycarbonyl to react directly with the chalcones. So for starting with, so in this reaction scheme, each of these lines over here will represent carbon monoxide ligand. This is for simplicity. Now, so our starting materials will be tri-osmium polycarbonyl and 2 equivalents of trimethylamine and oxide with acetonitrile as a solvent, and is reacted in room temperature. This is our expected product. So what happens is the oxygen in the 2 equivalents of trimethylamine and oxide will react with the carbonyl ligands here and here. So this will form carbon dioxide, which will then be released. This leaves 2 empty sites for the acetonitrile groups to bond to, which effectively replaces the carbonyl ligand. So this is what we'll get. And so here's the image that we took during the reaction. So basically, in this image, we are passing nitrogen through the system to ensure that the environment is deoxygenated. So during the reaction, we observed that the color of the solution changed from yellow to dark brown. And after we remove the solvents using rotary evaporation, we obtained 0.08 grams of dark brown solid in almost quantitative fluid. So for our final synthesis step, we shall be reacting the chalcone that we obtained earlier with the osmium carbonyl cluster. So the solvent we used was dichloromethane, and it was performed in 40 degrees Celsius. And this is our expected final product. So after we performed this reaction, we separated the products using column chromatography, as shown in this image, and we obtained a major product of 0.052 grams or 54% U. So after we obtain this final product, we shall be analyzing it using the following methods: infrared spectroscopy, mass spectrometry, and 1H NMR spectroscopy. So first, this is our IR spectrum. So here's how we're representing the results. Please direct your attention to these two peaks over here. So if you look at this weaker peak over here, we'll be representing it with its wave number, which is 2113, followed by W for weak. So for this stronger peak over here, we shall be writing its wave number 2063, followed by VS for very strong. So on the left column is the collated results of our major product, and on the right are the literature values of another compound, which is also a carboxylic acid group bonded to an osmium carbonyl cluster. Now, if you compare these values, if you compare the wave numbers and strengths, we realize that they are very similar. Thus, from this IR spectrum, we can conclude that the carboxylic acid group has been bonded to the cluster as we have expected. Now, next, mass spectrometry. So after doing some calculations, we expected the relative molecular mass of our product to be 1,118. The mass spec peak showed 1,119, which is what we would expect of the protonated form of our compound. This is the value that we expected, and from this test, we can conclude that the various components of our compound are there. So finally, we'll be using NMR spectroscopy. Here's our NMR spectrum, and here is our expected final product. So what we did was we did a comparison between the spectrum and our product. So the presence of the hydride over here is confirmed by this peak in the negative region. The hydroxyl group over here is confirmed by this peak. And if you add up the integration ratios over here, they add up to 10, which is exactly the number of hydrogens that we expect in this part of our compound. So from NMR spectroscopy, we can conclude that the hydrogens are in the places that we expect. And from these three tests, we can conclude that it is highly likely that we have obtained our product. So we believe we have successfully synthesized the chalcone-ligted osmium carbonyl clusters, and encouraged by this, we went on to synthesize an additional chalcone in preparation of making more chalcone-ligted osmium carbonyl clusters. So here's the additional chalcone that we synthesized. It is the 4'-hydroxy, 4-carboxylated chalcone. The reaction scheme is similar to that of the first chalcone. The only difference being the starting material for this was changed from 2'-hydroxyacetophenone to 4'-hydroxyacetophenone. The OH group was moved from here to here. So these are our expected chalcone, and we managed to obtain it in the form of a light yellow solid. And the melting point test showed that we had a melting point of 282 to 284 degrees Celsius, which is very close to the literature value of 282 to 283 degrees Celsius, again indicating that it was pure. So the U that we obtained was 77%. So for our future work, we shall be reacting the chalcone that we just obtained, the 4'-hydroxy, 4-carboxylated chalcone with the osmium carbonyl cluster. And then we'll synthesize more carboxylated chalcones and react them with the osmium carbonyl clusters. And we shall take these osmium cluster products and characterize them. So in the end, we hope to test these osmium cluster products for their properties as bioimaging agents. So hereby I come to the end of my presentation. I'd like to give special thanks to the organizers and sponsors of the 10th Rank Contest on Chemistry for High School Students, And I also like to thank Professor Nakazawa for inviting me to this wonderful event. And I also like to thank Professor Hong and Professor Leong from Singapore for their help. So once again, I'm Liu Shuliang from Chong Institution. With an image of our school's clock tower, which is the front facade of our school, and also a national monument. And this is Singapore. This is the image of our central business district. So thank you very much. Arigatou gozaimasu.
ありがとうございます。では何かご質問などございましたら、挙手をしていただければせっかくの機会。では、マイクをお待ちいたしますので。
So thank you very much for your interesting talk. Just a simple question. So in order to introduce the chalcone framework, chalcone unit into the dry osmium framework, you introduced one hydroxy group and one of the two aromatic ring. Okay? So you introduced the one carboxy group and one of the two aromatic ring.
Sorry?
One of the two aromatic ring. Okay, you have another aromatic ring in the chalcone molecule. So how about another aromatic group for the carboxy group introduction?
So for this reaction, there's a carboxylate group in our chalcone. So we know from publications that it will bond in this way to the osmium carbonyl cluster.
My question is, what happens if you introduce a carboxy group to different aromatic rings? Is it possible?
Introduce the hydroxyl group to the other benzene.
Carboxy.
Or the carboxyl group, change the position or introduce to the other ring. If we change the position of the carboxylic acid group, we intend to do that so we can synthesize a series of chalcones. We believe that it's possible even if we change the position of the carboxylic acid group.
Thank you for interesting results. First of all, I was surprised that you used osmium plaster because it's very expensive. Besides that, you studied from the osmium trinuclear compound, and you converted it into the acetonitrile compound.
Yes.
Then you introduced the chalcone. And it is known that the carbonyl ligand can be easily dissociated under the UV light irradiation. So what I'd like to ask you is that if you treat the triosmium compound in the presence of chalcone and the photo irradiation without acetonitrile, have you tried that reaction?
No, we have not tried that reaction.
So if you try that photo and radiation reactions, you may prepare the final result without one step.
I think there's something more we need to. Thank you.
Okay.
ありがとうございます。その他ご質問がございましたら、ご指導お願いいたします。質問の方はよろしいでしょうか。それでは以上とさせていただきます。主案龍さん、ありがとうございました。